Good afternoon, everyone. First of all, I would like to thank Dr. Umesh for asking me to be here. I have a very strong disclaimer, just like Dr. Vaibhav was saying, that I don't know statistics. But I do studies. My job it is to design and make my residents do projects, and I have my own institutional, like investigator-initiated projects also. So I do something, okay. But I have no claims to be a statistician. So I hope you will reserve the tough questions to the chairpersons. The other one is the font seems to have changed on the slides. I hope it has not changed too much. No, not moving. No, they are not. Yeah. No. Yeah. So next 35 minutes, I will be talking briefly about each of these. So what are the, first of all, I will have spent a couple of slides on the types of observational study types, not in depth, then briefly about the what we mean when we do estimations and hypothesis testing, which will come in the P value and all. I'll not be discussing that because I think there is a separate session on that coming up. I would probably spend some time on sample size because that is, I think, is a real life issue, again not in deep discussion, and bias and confounding, and briefly about analytical techniques. This using a data which we are right now analyzing in my department. So observational studies have its own value, like he was already telling, when RCTs may be inappropriate or impossible, and the only caveat is that when we do whatever, especially observational studies, we need to be very careful about the problems which can be there, and I think it is important for us to know even in advance whether this can be avoided or can be adjusted for later on when you analyze the data also. The three observational studies, I am sure we are all aware. Cross-sectional study, Dr. Keskar already referred to that. Case control study and the cohort study. This image briefly, those who may not be aware also, gives a description of what it means. Cross-sectional basically means it is a snapshot. You, at one time point, you look at whatever you want to, how many of your patients are having PTDM, how many of your CKD patients are hypertension at one point of time. Prospective cohort is where you have, you create a group. We are right now doing an ICKD cohort where you enroll people with particular GFR between 30 to 60 or whatever it is. You want to look at outcome of PTDM. So you recruit people with that, then you follow them over time, and then you look at their over time what is their outcomes. You will, all of this will be predefined. What exactly you will be looking at, what are the outcomes you will be looking at, all those things will be, and what analysis that you will do at what point of time will be predefined. Case control study is usually is a retrospective where the things whatever has happened already happened. For example, the typical example given is if you look at statistical examples is lung cancer. You look at people who have lung cancer, then you compare it with a group of people of similar background who didn't develop lung cancer, but the smoking has happened in the past. The whatever has had to happen has already happened, right? So other thing is then the cohort study can be prospective or a retrospective. I'll give you an example, right? What we have analyzed is retrospective. Cohort can be, for example, what we looked at is outcome of deceased donor with living donor transplant outcomes. So this is a we have done transplant, and right now we are looking at it. So this is a retrospective cohort. When these people got transplanted, it was either a deceased donor or a living donor transplant, and now we are collecting the data, and these are cohorts, because disease donor transplant is a cohort, living donor is a cohort. So this is a retrospective cohort. Similarly, it can be a prospective cohort also. Prospective cohort, of course, is a better design. So there are different forms of observational studies also. I'm sure you would have heard about estimations. Estimations basically is the descriptive sort of things we do. It is a numerical value. Basically, whenever we have the data, we describe how many of them are male, how many of them are females, how many of them are hypertensive, what is the GFR, how many of them had dyslipidemia, all those things. So these are described in proportions, rates, and means. Okay, or it may also give you effect. For example, what are the chances of somebody developing antibody-mediated rejection compared to other group. I'm telling you, say, difference between somebody who was given induction, not given induction, or between the deceased donor group and living donor group. Okay, these will be expressed in relative risk or odds ratio. We'll be discussing it briefly later on also. So this gives you three things. One, there is a association. Then it gives you the magnitude of that association and how precise is that estimate. So there are three aspects to it. One is whether there is an association, how strong is the association, and what is the precision by which, what are the chances that it's actually, what you have found is actually true. Okay, there are three aspects to this estimations or the data we present. Hypothesis testing is when, again, you must be doing it like you have a research hypothesis, you form a null. Basically what you do is you form a null hypothesis. For example, you want to study the efficacy of entry-coated budesonide. So your null hypothesis is that there is no effect. Right? It doesn't make any difference with regard to outcome, and then you disprove the null hypothesis, whereas the alternative hypothesis is that this makes a difference, or the proteinuria improves, or the GFR improves, or the patient, or the renal survival improves. So that is the alternative hypothesis, right? That is where you use various analysis, and then the p-value comes in. I will not be going into the p-value because I think that issue all of us are aware, and it will be discussed in the next session, I believe. So let us go to the study which, or the data which we are trying to analyze. I will be using this to explain the ideas of the concept of confounding and the other parts. This was the title. This is one of my residents collected the data, went to a PSM resident, his friend, and got it analyzed also. Okay, so the title was Patient and Graft Survival Outcomes of Deceased Donor Kidney Transplant Compared to Living Donor Kidney Transplantation, a retrospective study. Basically, what he needed to do was, we have done around 330 transplants so far, approximately around 100 of them were deceased donors. So he wanted to compare the outcomes of, basically what he wanted to cover is survival. Okay, how many of them had graft loss and other things, and this is the title he has written for it. I would say, let me say, I don't put it on the resident, let me say, this is the decided, we decided. Okay, so do you think this is okay? You want to modify it in any way? Because he already mentioned a PICO, what is that? PICO format, right? So based on that, okay, it's to save time. So this is how we changed it. Okay, this was the initial plan, then we changed it to comparison of patient and graft survival outcomes between deceased donor and living donor kidney transplantation, a retrospective cohort study. Right, so here the population is who? The people who have undergone kidney transplantation. Right, intervention is what? It is deceased donor and living donor. Right, outcome is what? Patient and graft survival outcomes, right? And then a component of the study design which is also desirable, you can, he just mentioned as retrospective data to add more respectability, we have added, which is true, I will not say it is true, it is actually true that this is actually a retrospective cohort study, right? So, but what is the role of comparison here? Is it okay if we don't have this comparison in the title? Patient and graft survival outcomes. Can we leave out comparison? It should not, we should not. It is better to have the comparison, because when we say patient and graft survival, there is no analytical component to it. Right, we will say that the living donor outcome, living donor survival, say mean duration is 8 years and deceased donor is 10 years. But we are not analyzing, we are not telling whether this 2-year gap is a significant one, whether it is significantly better or not. So by adding this comparison to the title itself, you are also giving the idea that we are actually going to say, and then we, okay, that also means that you have to design it properly to bring in sufficient statistical power to this thing. So comparison, I would say, makes it complete even more, right? So this is an example of how we change the title of the study. I will be telling more. So this is basically the PICO format: population or problem, intervention or treatment of interest, comparison or control, and the outcome. Going on, this was one survival analysis from the study. Okay, this is a Kaplan-Meier survival estimate. And the blue stands for living donor transplant, and the red one are the outcomes of deceased donor transplant. So can you think of any problem with this? not be a problem, but are you okay with this or? Yeah, so disease genre, so that is, I think any nephrologist will object to that. But unfortunately, fortunately, this is true for our patient population. We'll be coming to that, but that is one. So on the face of it, we will not believe this. Agreed. So we have to check whether there's something which went wrong. Anything else? The other thing is that it is not touching the median. That means that for any survival plots, to the best of my understanding, people can correct me if I am wrong, it should have sufficient follow-up. So that means that the half line has to be met. So what it means is that the duration should be more than at least half of the people have graft loss. Right. So that means that the graph has to touch the midline. Right. I don't know whether I did something, said something wrong.
No, Sreejith, I don't agree with that because Mike. If, as you said in the examples, that you have an 8.
I think it's not on.
So, if, for instance, you have a long follow-up of 8 to 10 years that you expect as your median, you might still want to analyze at 5 years if there is a difference. Yeah. So I don't think that's necessary to wait.
Yeah, so that point is well taken. So I didn't mean that it is necessary. We have to be more careful while we are analyzing that report, or we should not take it for face value because the expected duration follow-up is not there. A good duration is when at least half of the patients have reached the median period. That's all what it meant. It doesn't mean that analysis is not valid. No. The value is a little less, that's all. Okay, that was the point I was trying to make. I'm sorry if I was unclear. Right, so this obviously raised questions whether this disease donor outcome is better or not. So let us look at the other thing. So what about the sample size? One by one we'll go. There were a total of 266 transplants. This is still 2022 end. 22 and we had collected the data. So total 26, out of which 172 were living donor and 94 were disease donor. So don't look at the other thing. I just put it up because I copied a. So is this a good sample, or what is the student's view? Is the sample good enough or it is not good enough? It should be good enough. Okay, no, so that's not how we decide, right? We look at many things. So what do you mean by, so this concept I think is very important. I want to discuss a couple of slides on this because even day in and day out, because most of us, I'm sure, reviewing papers for journals also, sample size calculation is mostly non-existent. Most of the cases, even if you raise a question, the reply will usually be that it is a convenient sampling, but convenient sampling is not, it is a sampling strategy, right? It's not sampled, right? So having a right sample is extremely important. That is central to our any research we do, because what we are essentially doing by sampling is that we can't, sample is supposed to be representative of the population. We are taking say transplant patients and you want to study something, outcome or whatever. You can't include all the transplant patients, all the diabetic patients, right? So you will take a representative sample. So it is important that the sample which is taken is, one is representative, right? What is the problem, what is the common drawback which is usually discussed with regard to say maintained trial and arms trial? There is a difference, right? What is that? Maintained trial is largely Caucasians. Okay, there is no African Americans, Asians, whereas it is more racially diverse, so it is believed to be more generalizable, so it is representing the population. The sample in the trial is more representative of the larger real world population, right? So the sample has to be, the first point is it has to be representative in character. Second thing is that it has to be sufficient in size. Okay, so to ensure that the sample is representative, you have to use a proper sampling strategy, right? So that depends upon the study how you do. Most of these, say for example, this some trial you are doing, you may do all consecutive thing, or you will randomize, whatever. So there are different stratifying and the convenient sampling is a sampling strategy. It is not, it doesn't tell you anything about the sample size, right? So that is a convenient, because that is whatever is available, what is practical you do, that is a sampling strategy. It has its own problems. Sufficient size is needed for this to be, so there is, whenever you take a sample, the findings are likely to be slightly different. So this is the sampling error, there is a difference. Our effort is to minimize the difference between the sample we are studying and the real world population, right? For this, the sample has to be representative and enough in size, statistical power has to be there, I will come to that. So to minimize the sampling error, right? So how do we do that? You calculate the sample size properly, right? This is the sample. So for a study like this, where we have retrospective cohort, you have only 266 patients, and you have so many things. How do you calculate sample size? You can't really calculate sample size. What you can do is a postmortem, where you will calculate the power, whether the data you have is powered, has enough power. So there are two things, like one is power, what is the other thing? Yeah, so usually you will set values like 95% and 80. So any power, so this is the power analysis for our data. There was a significant difference between group 1 and group 2, which was this is at 6 years, 90 and 75%, and it is coming to 86.5. What does it mean? The power is good enough, right? So this is basically retrospective. We have the data in hand, we have to analyze, there's no other way. But still, suppose this comes as 60%. What does it mean? Probably we should not be analyzing and publicizing that data, because it is not representative, right? It is misleading. It is likely to be misleading, doesn't reflect the reality, right? Okay, so the point I'm trying to make is calculating sample size is extremely important. It is best done when we do in the beginning itself. For example, let us say I wanted to do a study on factors influencing the development of PTDM in transplant recipients. Right, what are the factors influencing PTDM? So I calculated sample size. How would you calculate sample size? For that, you will know this is basically a, I would say, a case control study, sort of. No, it is a case control. Basically, you will look at how many of them developed PTDM and didn't develop PTDM. So basically, you will look at what is your incidence, or what is the literature incidence. We have looked at our incidence of PTDM is 30%, 30. It is high, right? So when we calculated, we made a plan, we wrote the proposal, but the sample size was coming to almost 450, 500. And we were doing on an average around 30 to 40 transplant in a year. So it will take me 10 years to recruit enough sample, and the plaque people we have to follow for 5 years. So we decided not to do the study, because we can't do. We can recruit say 100 patients in 3 years, but it doesn't have the statistical validity for you to come out with any conclusions, right? So it is important. What I am trying to make is, whenever you do a study, whatever it is not sufficient. For technical purpose, you can write that convenient sampling was done, but then that is not even calculating the sample, right? So that we should not be doing that. If there is one thing I want you to remember after this session, is to make sure that you do sample size calculation properly for all sort of studies you do. All of us should be doing, right? So this observation is true. Let's come to that. Time is there. Okay. So the living donor, we all know that living donor outcomes are much better, because there is no DGF, there is a better HLA match. Why is this data, why is our study showing that deceased donor, this thing is better? So these are again some this thing from the tables I took out from that analysis whatever we are doing. So there are a few things which stands out. What is this? The mean donor age was 43 in living donor, and it was 36. So there is a 1 decade difference between living donor and deceased donor, right? And younger donor is better to have, right? Next thing, we have a policy of institutional policy of giving thymoglobulin induction to all deceased donor transplant. So almost 100%. So it is 95%, I believe, in has received deceased donor. 95% has received induction. And whereas in the living donor, our general policy, because we do only near relatives, most of them are low risk, so no induction. The spouses usually get basiliximab. And some of the living donor who are found to have immunological risk, or they ask for it, they will get induction, usually basiliximab. So what you have two groups. One is deceased donor, one is living donor. Deceased donor, everybody has got thymoglobulin induction, and that too we give minimum 3 milligram per kg. Right, and then you have on the other hand HLA better outcome supposed to be who don't get any induction, and if they get induction it is basiliximab, right? So there is a problem, right? And there is more, delayed graft function. one of the reasons why outcomes following deceased donor outcomes are poor is primarily attributed to delayed graft function. DGF may be various reasons, there is the cytokine storm in the donor, AK in the donor, a lot of things goes on, and the outcomes are poor primarily because of that. But there is no difference in the DGF rate between deceased donor and living donor in what we have done. There is a reason for that, because 100% of our deceased donor are in-house. It is practically like a living donor. We certify branders, by that time we will get the recipients ready, and we take the deceased donor to the OT, take out the kidney and put it into the deceased donor. There is if the mean of, okay, something else is coming. So the cold ischemia time is longer because we do both the kidneys are transplanted in-house. So for the second kidney, the cold ischemia will be lower. That is why the cold ischemia time is longer. But then there is no difference, and the incidence of DGF is around 10%, be it living donor or deceased donor. So that risk factor for the deceased donor is also taken away, right? And rejection rates, actually the rejection rates numerically is statistically there is no difference. But if you look at it, the ABMR rates are lower in the deceased donor compared to living donor. Statistically not different, right? Okay, but you should keep in mind there is some literature showing that if you use ATLG, theoretically we don't, ATG, we don't expect, but then our data actually shows that there is reduction in ABMR happening in the deceased donor compared to living donor, right? And then normally, who are the donors, who are the recipients? 80% are women, 80% are men. But what about deceased donor? 70% are men. And there is at least some data saying that when the donation is from a male to a female, the outcomes are better. Maybe because unlike the other way around. Okay, when you compare gender-wise donation, maybe something to do with the body size or the glomerular number. So, what are we finding? Even though they are supposed to be two groups, their difference is not only with regard to the donor part, right? They are completely different with regard to induction, be the age of the donor, the direction of the donation, the rejection rate statistically is not different. So, there are so many confounders. So, what are confounders? Confounders are those things where you have decided an exposure, which is deceased donor transplant, right? But there are other factors which independent of that influence the outcome. So these are all confounders, right? So younger age, we already discussed this. So we will go to bias and confounding. So there are different types of bias and confounding: selection bias, information bias, and then confounding. Selection bias is usually for poor sampling strategy. Your case differentiation is not proper, case differentiation is not complete. You decide that you will take all consecutive samples, but the sampling happens only when the resident feels like right. So there are selection biases in that. There may be measurement error. There may be here also the antibody-mediated rejection rates were initially found to be higher in living donor, then it was found that the data was reversed, right? So all sort of things can go wrong, so we have to be clear with that. There are a lot of things which can result in bias. Then confounding, I already mentioned that the confounders are factors which independent of the exposure influences the outcome. We'll go on to the analytical technique. So what to do? Suppose you have in this patient you wanted to analyze, but then after doing all these things you found that there are a lot of factors which are independently, so you have to do something, right? We can't go back and change it. If you are planning the study, suppose we had planned it as a prospective study, we would have done something. Okay, we would have done some sort of adjustment or matching or subgroup analysis well in advance, so that you will be able to find the difference. So we will discuss now what to do for this patient. There are ways to deal with this confounding also. One is matching. Matching is what? So one matching we tried in this, I am not going to details of that, was basic difference was supposed to be HLA not there and HLA, we do HLA for all living near relatives, it has to be haplomatch, otherwise we send them away because we don't do unrelated. Okay, so we are assuming that spouses are also HLA mismatch. There is no HLA match there. So spousal donor and living donor is HLA matched. Spousal donor is a living donor, but HLA mismatch is not there. So there is some comparison you may be able to do, right? So there are multiple factors. So you basically can match regard to, for example, simple examples: age matching, gender matching, diabetic status, or you can compare with regard to CKD stages. So there are different strategies to match the groups and then do analysis. Limitations: when you do this, your sample size will usually come down and the statistical validity may be lost. So, and there may be overmatching also when, unless you are using clearly defined confounders, you may end up overdoing it, and then you will introduce new biases in that. Stratification is what I was referring to. You stratify based on specific confounders, diabetic, obese, CKD stages. So you can subcategorize, and stage wise you can compare the groups. I'm not sure how this thing came in between, like, okay. Yeah, I did something. I don't know. Anyway, we'll leave that. So there is something called propensity score. So here if you look at it, where was that? Yeah. So this is, I'll come back to that. So if you look at it, these are the things which were supposed to influence the outcome. So there are, in that particular study which I told you, there are so many confounders. So what to do? Most of the matching and all you cannot do for so many. Okay. So when you have so many confounders, what you do is something called propensity scores. Okay, I don't know, I have not done this, but then what you do is basically for each of them, for each of the case, you calculate a score which will capture all the confounders, and then the scores are matched between the two groups, right? So there are statistical ways to take care of confounders, provided you identify them or you know them, right? So these are different strengths and weaknesses of each of them. So matching, stratification, multivariate adjustment, and are different ways to take care of confounding. Multivariable regression is, again, I am sure you are all familiar with multivariable regression, but then I would say we have to be very, very careful, because it depends upon the data, and then you have to use the correct. So there was a problem with this one. For example, this Cox regression was done. We'll come to that why Cox was done, but then it showed that there was the only determining factor was the ABMR, and those who had ABMR, significant factor was ABMR, and those who had ABMR had a twofold higher risk of graft loss. But when they did the analysis, what they used was not the time dependent analysis, where you take the time to graft loss, whereas it was taken as those who had graft loss and no graft loss, those who had ABMR and no graft. So that is not where Cox regression should not be done like that. Cox regression is, so we will come to that. So there are different ways of analyzing it. So for binary variables, again the font has changed somehow, I don't know how. This is not a font, I had put it there anyway. So binary outcomes, for example, you have infection, rejection after kidney transplant, rejection, no rejection. Okay, that is binary, yes or no. There you use logistic regression and you express it as odds ratio. Odds of something happening in one group compared to the odds of it happening in those group which is not exposed. Right, we'll come to that again in another slide. Continuous variables like EGFR level, creatinine, TAC levels, you use linear regression and then you show the mean difference. Time to event is when you use the Cox proportional hazard model and then you express it as hazard ratio, right? So when you have survival analysis, there you are expressing in terms of time dependent. There you will use Cox regression, whereas here that was what is intended, but then the data point used was whether graft was there or not. So that also was not, because it is a binary variable. There you should not be using Cox regression. So the point I am trying to make is, we need to be aware of, there are models which are required for certain data sets. It's important for us to, I would say, state in the paper also. Let me look at it from, I'm not a statistician analyzing it, but when I'm reading a paper, I think the author should write what model he is using and why he used that. If it's a time dependent model, for example, use a Cox regression. So that has to be stated in the paper. We should be looking for it when we read the paper also. Odds ratio, quickly, how many minutes more? 10 minutes are there, okay. Odds ratio, as I told you, is odds of something happening. For example, smoker, non-smoker, cancer, no cancer, right? So what is the odds of cancer developing in a person who was a smoker compared to the odds of cancer developing somebody who is a non-smoker, and then you calculate the odds ratio. And odds ratio for a non-statistician, you look at the value whether it is less than 0, less than 1, more than 1, or equal to 1. If it is more than 1, there is a higher odds of the outcome. If it is less than 1, you will say it is protective. And basically, if odds ratio is 2, then it means that there is a 2 fold risk of developing lung cancer following smoking. And the confidence interval is what give you, so I was telling you, one, it will show an association, second part, how strong is the association. So here you are telling that it is 2 times, and then how precise it is. The confidence interval will tell you how good it is, right? So it has, if the consider, normally it is usually taken as 95%, and if you know, you also know that if it crosses 1, then that is insignificant. Practically we use odds ratio when we use case control studies and logistic regression analysis. There is something called relative risk or risk ratio, where you are comparing incident rates of events in 2 different groups. Again, it's similar in the sense you look at it whether it is more than 1, less than 1, equal to 1, and accordingly you decide whether the incidence is higher in the exposed group compared to the other group. And it again will tell you, if it is 1.5, then it means that it is 50% higher. So here also you are getting a association, the quantum of the strength of association, and it is usually used in cohort studies. Hazard ratio is when there is a time dependent event happening. So it is the hazards of the hazard rate is right at which this event happens over time. Again, it is 1, more than 1, less than 1. For a non-statistician like me, that is simple. Okay, I am not a statistician. If somebody has anything to add, I would request you to add to this. When interpreting, basically, hazard ratio is commonly used in clinical trials, and when effectiveness of treatment over time has to be reported. Right, and it is usually represented by Kaplan-Meier curves. I will end with one more thing. This is the stop statement. I am sure there are different guidelines or framework given to when you are reporting observational studies, RCTs and all those. So stop statement is for observational studies. So there is a long list. So when we are, I find it useful when we are analyzing papers also. There are things which checklist is there which are supposed to be for each component of the paper. We are supposed to follow certain things. Right, so I will leave it for you to read. I will not be discussing it here. So that's all I have today. I was trying to talk from a, as I mentioned, non-statistician point of view, based on the actual problems which I also face when, be it a project done in the department by a resident, under my guidance of course, and when we are reviewing papers, right. And one single takeaway I want to impress upon everybody is about the sample size, which I feel is a very ignored issue, and but that is central to all sort of studies we do. Thank you.
I think
many new things. 2 points I want to comment. One, and both of these points are for youngsters, not for the experienced people here. The 2 points are, although Weber as well as Sreejith have shown that observational studies are in the lower end of the spectrum or the pyramid, the bulk of the data comes from observational studies. So don't ignore observational study. In fact, there are many good data which has come from observational study, which has actually led that, okay, now no RCT is required in this, because we have such a strong observational data that we don't even require an RCT. So the point here is that observational studies are equally good, although they may be at the bottom or middle or whatever at the pyramid, but they are equally important, and the bulk of data comes from observational study, and that is why this presentation is very important, that how you analyze this observational data. And the second point is about sample size, and Sreejith has repeatedly mentioned, but I sort of disagree with that statement. The reason is, it is always good, to calculate sample size, particularly if you are doing good trials, RCTs, and good cohort studies or good case control studies. But observational studies are meant to generate data, irrespective of your sample size. Why I am saying so? So again, I am not denying that you should not calculate sample size. Always try to calculate sample size and always try to meet the sample size criteria. But suppose you have a research question in mind and you don't have sufficient, you have calculated, and you feel that I will not be able to generate that much of sample size. So should you not be doing that research? Of course not. So the reason is, you should generate the data, and there are ways of presenting that data. Like for example, you can start with a case report, for example. You can start with case series, another level of, then you can do a pilot study. Again, all these are the studies where no sample size is required, right? So you can start with different kind of studies to just come out with the data, because data generation is more important, and then you will be putting that in your limitation, that this is that kind of data where no proper sample size was generated, so this has to be replicated. And many times again it has happened that data has started from case report to case series to pilot study to move to good cohort study and then finally randomized studies. So I think these are my points.
Yeah. So you have made a very valid point, because if you look at historically also, some of the landmark papers were actually large case series. There's no doubt about that. And if you look at my own papers, the most I think impactful paper, or which got published in Impact, is some paper on CKDU, where it is nothing but a very long case series of around 2,000 patients of CKDU. Okay, that also I would say the impact also. This I'm learning from the scientific impact, but then reporting it and all is actually impactful. So I'm not saying that we should not do. The only point I was trying to make is that when many people, at least we know, you are doing it with a knowledge that there is a limitation and I am doing this for this reason. But I believe many people are not doing it that way. They actually are doing it thinking that they are doing the right thing. That is the point I am trying to make. When somebody is doing a study and IgA nephropathy and say 80 patients or 150 patients are recruited, and then outcomes are reported and saying that steroid treatment is better or not better, they have not attempted sample size. In that there is a problem. So that is the point I am trying to make. We need to look at it. We may not find that the sample is adequate, or when you look at retrospective, for example, the power is not adequate, but then we are finding something, we may still report it. I am not saying, but the value is not as good as a sample was adequate and the power was good. Yeah, I agree with you.
Building on what Dr. Manish said, if you go back in history of epidemiology, the first study which brought epidemiology to forefront was Dawn and Hill's study on smoking. Till now we don't have any RCTs done on smoking telling that it causes cancer. So all the data is from the observational data itself. Strictly speaking, meta-analysis is also an observational study. So observational studies have got their own value in their this one. And second, association and causation. Here actually, instead of sample size, probably the magnitude of effect is more important than having the sample size. If magnitude of effect is higher, for example, if you take grade guidelines, when we are going to grade an evidence in observation studies, so one of the thing is large odds ratio. It will move the grade to a higher level. To lower, we start with lower certainty, then we to move to moderate certainty when the effect size is large. So that way sample size is important, but if your effect size is big, then sample size will not matter much in the end.
Okay.
Yeah, I think in retrospective studies it gets very difficult to determine the sample size, because ultimately in your study itself you had 266 patients, so you had to analyze this data. So it's very prospective studies, yes, sample size becomes very important, especially because then you determine that this would be the sample size, knowing from a previous study that this is the kind of an effect difference that you want to see, and then based on that difference you decide that this would be the sample size. But for a retrospective study, I think sample power of the study and limitation of that study would obviously, and you have highlighted this very, very effectively. And I think what we need to understand is what is being talked by Sreejith and Manish. And Manish says that observational studies are important. They are important. There is no doubt about that they are important. And the question is that the person must know the limitations of what is the message that is coming out of these studies. And in randomized trial, there are unknown biases. These were known biases. But there are hundreds of unknown biases which get into observational studies. Unfortunately, many of them these confounders cannot be taken care of. So that's the reason why the value of this. There is no doubt that a lot of science has moved from observational trials itself, and a lot of science is learned also from observational, and you plan a randomized trial only. But what we should as a community, I think in India, do is build on multi-centric observational trials and then move to multi-centric randomized trials. I think that is where we are lacking, and I think I don't know, Indian Society of Nephrology, Indian Society of Organ Transplant, these have not been able to do it. Somehow as an individual we do very well, but as a community somehow we've not been able to create that kind of an environment. And I think the solution would be for numbers, would be to create it multicentric. In one center is not going to be, but one has to agree that you do prospective observational trials, pick up 6-7 topics, each center picks up one topic and the other center maybe picks up as a central coordinator for those trials. And I feel that probably that's what we need to do, is improve observational trials. I don't think we can do only random control that. They're not going to be easy because it requires a lot of money. Observational trials don't require that kind of funding because it's basically trying to sort of sort out some of the confounders basically in prospective trials, whereas in randomized trial you need a lot of money. So I think it is these kind of things which will move us ahead in these kind of studies. I think otherwise the points you made is very valid, that observational trials obviously are important, but I think we should do also more randomized trials as well. It can happen only multiple.
Yeah, so the bad naming of observational studies have gone to some extent. I have actually heard somebody saying that I do only RCTs, I don't do any observational studies. So I think that is a problematic sort of thing.
Because HIV was a case series.
Yeah.
A lot of first literature will come from case. Ultimately, hypothesis will develop only from case.
Yeah, I think we have many more Maharathis to give their comments. Dr. Hasse, Dr. Val, anybody? We have 5 more minutes to discuss. And students, whether any questions from your side, this session has given us enough time for interaction.
Dr. Sreejith.
I entirely agree with the chairpersons. Observational studies are important, and it should be multi-centric so that number will increase. And all research has started with a case series. Like 1980, HIV/AIDS was reported, and then it is a basic requirement, then case series, and then cross-sectional, and then going to systematic review and meta-analysis. To improve the observational strength of observational study, we require a multi-centric thing.
Dr. Sreejith, you two things. One is you indirectly introduce the concept of errors while talking about sample size and effect size.
I didn't want to talk about it.
PAR and type 2 error got
Yeah.
cleared, but alpha error or type 1 error is actually more important. So if you would care to say something about that one. And the second was that when there is a null hypothesis, as you said, there is an alternative. There is not one but two alternate hypotheses. Because we are trying to say that our intervention is better than standard of care, but it might actually be worse. And there are trials which have shown that. So a member of the Mumbai Nephrology Group taught me a quotation from Huxley some years ago. He said, "The great tragedy of science is that a beautiful hypothesis is often slain by an ugly fact."
The other necessity to do multicentric trials is we have seen in lupus where different ethnicities are involved and something like lupus where only Caucasians are there. Even in our country we have our ethnicity is different in different parts of the country. The northeast is entirely different. The north behaves entirely differently. The south behaves entirely differently. So ours will be a very good multi-ethnic cohort, in fact.
Thank you so much for such an insightful lecture.